Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on September 29, 2025, just yesterday. The big hook is that this paper introduces Visual Jigsaw, a self-supervised post-training task that markedly boosts vision-centric skills, including a depth benchmark jump from 48.66 to 64.00, a gain of plus 15.34. The paper is titled Visual Jigsaw Post-Training Improves MLLMs, and the implications for model training are quite significant. In short, the method uses an ordering game over images, videos, and 3D data, aligns naturally with reinforcement learning from verifiable rewards, and needs no extra annotations or generative decoders. Also, the author shared a GitHub repo. You'll find pre-trained checkpoints for image, video, and 3D Jigsaw on Qwen2.5 VL 7b Instruct, training scripts and train scripts, evaluation guidelines and eval, and dataset pointers for COCO, LLaVA video, and ScanNet. There are requirements and setup files, examples and assets, and docs, with inference matching Qwen's code. Alright, Figure 1 introduces Visual Jigsaw as a simple puzzle-style post-training that upgrades perception across images, video, and 3D. The left panel sketches the task metaphor, where pieces must be ordered correctly, which mirrors the permutation objective used in training. The three radar charts on the right compare the method against the dashed Qwen2.5 VL baseline, and the solid shapes expand outward, signaling stronger scores across fine detail, temporal direction, and 3D geometry. Together, these visuals emphasize cross-modality generality because one training idea benefits diverse benchmarks. Alright, Figure 2 shows the core idea in action. The model learns vision by solving ordering puzzles, which means predicting the original permutation of shuffled parts. This overview highlights three variants, so the same rule spans different modalities. The image jigsaw panel cuts an image into a grid and asks for the raster order. The 3D jigsaw panel ranks sampled points from nearest to farthest. The video jigsaw strip shuffles clips and requires the true chronology. So while Figure 2 sketched the jigsaw task, Table 1 reports how it translates into accuracy on image benchmarks. The takeaway is that image jigsaw consistently beats the base model and the other reinforcement learning baselines across perception, spatial, and compositional skills. Fine-grained perception jumps, with MMVP up by about 6 points. Spatial understanding rises as well, with DA2K gaining about 6 points because ordering pieces refines relative distance judgments. Compositional understanding, which tests tricky text-image pairings, improves as Wino-ground GACC climbs by about 2. So, while Table 1 focused on images, Table 2 reports video benchmarks and shows that the jigsaw training improves results across diverse tests. This table uses multiple frame settings, for example 32 frames per clip, which probes whether perception holds under different temporal coverage. Across almost every column, the jigsaw variant surpasses the base model. Gains are strongest on tasks that require temporal direction understanding because clip ordering trains chronology. Cross-video reasoning also strengthens, as reflected by higher CV bench scores. So while Table 2 covered videos, Table 3 reports 3D benchmarks. It shows consistent gains, with the model improving depth comparison by about 17 points. The rightmost DA2K column highlights this because depth ordering pre-training, which teaches the model to rank near versus far, directly matches the evaluation. Other columns also rise by around 2 points across single-view, multi-view, and egocentric tests, which suggests stronger general 3D perception. Wrapping up, 2 takeaways stand out. A simple ordering game, trained with verifiable rewards, reliably boosts perception across images, video, and 3D without new decoders, labels, or architecture changes. And vision-centric post-training meaningfully complements text-focused reinforcement learning. The broader implication is scalable, self-supervised perception for multimodal systems. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.